We're going to continue on and finish up on section 8.3 today, and I'm going to start out with an example. I want us to look and see what happens with this integral from 1 to infinity of dx over square root of x plus 2. Okay, now a much simpler version of this would be the integral from 1 to infinity of dx over the square root of x, which we know is going to diverge because it's of that form, 1 to infinity of dx over x to the p, where p equals to 1/2, which is less than 1, so I know it diverges. Okay, now if you did not remember this part of it, what could you have done? You could have calculated the limit as b approaches infinity, the integral from 1 to b of dx over square root of x, and worked it out this way. And then you'll find this. Okay, and as b goes to infinity, this part of it goes to infinity, which diverges. So I know that this diverges, so I'm going to hope that this function is the smaller function, f. But what happens here when we compare these two integrals is that this one on the left, the one that we need to figure out, the denominator is getting bigger, which means the fraction is smaller. So I actually have this as my inequality, and this integral on the right-hand side is diverging, which means that the direct comparison test happens to fail, unfortunately, because this is now g of x and this is f of x. So what happens when we get something like this is that we need to show that these two functions are growing at the same rate. So if I compare 1 over square root of x plus 2 and 1 over square root of x as x goes to infinity, let's see what happens. I can flip this fraction, so I have square root of x over square root of x plus 2, and as x goes to infinity, the plus 2 kind of doesn't matter, so all I have is that this equals to 1, therefore the two functions grow at the same rate. This test right here is what we call the limit comparison test. This particular integral from 1 to infinity of dx over square root of x plus 2 diverges by what we call the limit comparison test, and I'll abbreviate that as LCT. So let me write out the limit comparison test, or LCT for short. If f of x and g of x are positive, continuous functions on your interval a to b, and if the limit as x approaches infinity of one function over the other equals to some number L, f of x and g of x converge, or both diverge. Alright, example 2. The integral from 1 to infinity of dx over 2x squared minus x. Okay, so let's see, what can we compare this to? So that's sort of our first step, is what to compare it to. It'd be much nicer to have simply dx over what? How about just a 2x squared? Let's ignore the minus x part. Well, this integral, even though it has the 2 in the denominator, I can factor that out and write it out as this. And this would be that same form as 1 over x to the p power, but p equals to 2, which is greater than 1, which means it converges. The denominator is getting bigger, so the fraction is getting smaller. So my inequality goes this way, and this is my f, whereas this is my g. So the smaller function converging, not useful. That's why we need to use the limit comparison test. So we're going to go ahead and try to show that these two functions grow at the same rate. So that means calculating the limit of one over the other as x goes to infinity. So I've got 1 over 2x squared minus x over 1 over 2x squared. So this is now just practice on limits. 2x squared over 2x squared minus x. This equals to 1. Therefore, they grow at the same rate, which means now we can write our conclusion. By the limit comparison test, dx over 2x squared minus x from 1 to infinity converges also. So notice the several things that we have to write out here. We do need to make sure, as our first step, we identify what we want to compare it to. We make a conclusion about the one we're comparing it to, so we say that it converges. The third thing is to actually show that they grow at the same rate. And then the very last and fourth thing is to say by the LCT it converges also. So you do have to say all 4 of these parts in order to complete the problem. Okay, let's try one more. The integral from 1 to infinity of 2 plus cosine x over x dx. Okay, so on yesterday's lecture I had talked to you guys about whenever you see one with a sine or a cosine, we're going to do something a little bit different. So here I'm going to start out with cosine x. Cosine is always bounded between 1 and -1. But now I'm going to try to make this middle part of my inequality match up with my problem, so I'm going to add 2 to it, and then I'm going to divide by x. That way I know that my 2 plus cosine x over x has to be bounded between a 3 over x and a 1 over x. They're very similar. We're going to go ahead and use the direct comparison test. I know that the integral from 1 to infinity of dx over x fits that form where p equals to 1, which means it diverges, and it's the smaller function. And if you had even chosen the 3 over x instead, well, it's going to diverge times 3, it's still going to diverge. So either one works. These two functions diverge, so therefore the middle one diverges also. So this one happens to be, by the direct comparison test, it diverges also. Okay, and I'm going to take a look at one last one. I believe this was on your homework the previous night. 1 to infinity, d theta over 1 plus e to the theta. So let's compare this to a much simpler function. That would be what? E to the theta in your denominator. So I'm going to go ahead and write out this limit. This is just going to be e to the negative theta d theta. So I can integrate negative e to the negative theta from 1 to b. Gives me negative e to the negative b plus e to the negative 1. And as b goes to infinity, notice it's a negative exponent, so this goes to 0, so my limit equals to 1 over e. So I get a number, therefore it converges. So let's check to see that they're growing at the same rate. So the limit as theta approaches infinity, because we're using thetas here instead of x's, of 1 over 1 plus e to the theta over 1 over e to the theta. Let's simplify out this fraction. So I have e to the theta over e to the theta plus 1. Well, the plus 1 doesn't matter. Both of these are going to infinity at the same rate, so this equals to 1. Therefore, they do grow at the same rate, and d theta over 1 plus e to the theta converges also.